So wrapping up our videos on graphing aggregate expenditures in Python, we take a last look at aggregate expenditures and then we look at the spending multiplier. So we started this series of videos of graphing aggregate expenditures in Python by graphing the aggregate expenditure function, which you see here. And if you're working along in the workbooks, just quick here, go to drstephpowers.github.io/econ in Python, and the workbook is here, aggregate expenditures. Again, click into Google Colab, log into your Google account, save a copy so that you can add and amend to the code. All right, so what we're doing is we're graphing aggregate expenditures. Well, throughout the videos, what we've been doing is collecting formulas. So we collected a formula for consumption spending, one for investment spending, one for government spending, and one from net exports. So if you followed along in the previous videos, I'm just going to scan a quick through here. We found a plot for consumption spending, and we found a formula 5 plus 0.6y. We did savings. We looked at disposable income. We looked at investment spending and found I equals 75. We then looked at government spending and we found our formula government spending equals 160. We also looked at exports and we found a formula for net exports. Just go to my last formula here of 60 minus 0.1y. Now, if you have a bunch of formulas for C and I and G and X minus IM, and you don't have the table of data we started with, you can still graph the aggregate expenditure function. And so you can use Python to do that, to do linear algebra. So what we're doing here is adding formulas. So we had our formula C equals 5 plus 0.6y. I equals 75, G equals 160, and NX equals 60 minus 0.1y. Well, Python has this lambda function. That's what you see there, this lambda. And this allows us to write formulas that have a variable, a letter in them, okay, and let us do things like sub in values for that letter and maintain that formula. So what we are entering here is the formulas that we've collected. So C equals 5 plus 0.6y, and we're putting it into Python using this equals lambda, and then y is our variable, and then colon, and then the formula that has the y in it. So C equals lambda, y colon, and then this is the formula that you found earlier. And same thing for I equals lambda, y is the variable, comma, and I equals 75. Notice here there is no lambda here, or sorry, there is no y here because there was a zero slope. Okay, G equals lambda y colon and then 160 because again there was no slope. It didn't depend on national income. And then we have our net exports equals lambda y colon 60 minus 0.1y. So this was the formula you found for net exports, and we're simply entering in these formulas into Python. So maybe we didn't have the original table, and all we had was C equals 5 plus 0.6y, I equals 75, G equals 160, and X equals 60 minus 0.1y. We could still end up with our aggregate expenditure graph that we started with. So we're entering the formulas into the system. Okay. And then I'm going to give it a formula for aggregate expenditures. And that formula for aggregate expenditures says that it's the formula for consumption, so C parentheses Y, plus the formula for investment spending, I parentheses Y, plus the formula for government spending, G parentheses Y, plus the formula for net exports, NX parentheses Y. So we can add these formulas together. They're all dependent on whatever the value of y is. That's our national income. And since we're giving it a formula where we have not given it a value for y, we write AE equals lambda y colon, and then just C plus I plus G plus X minus IM. What this allows us to do then is actually sub in values for y, and it will find the total spending. So for example, if national income, y is 400, then the aggregate expenditures are 500. If national income is 600, then aggregate expenditures are 600. Recall from that very first video, this is where we have equilibrium, where national income equals aggregate expenditures. What this means then is that if you have a list of values for national income, 0, 100, 200, 300, 400, 500 to 800, we could have it find the aggregate expenditures for all those different income values. It would take each value of national income and sub it into these formulas and add the formulas together. So let's tell it national income. And I'm doing that again here because in our previous videos, we had taken national income and reshaped it to do our linear regression. And we don't want that shape here. We just want it as an array. So I'm just copying this line of national income, and then I will convert it into an array. So now I'm going to create just this empty list here, x equals hard brackets, and we're then going to populate it. So what I want it to do is I want it to take each value of national income and dump it into this aggregate expenditure formula and find me the value. So I've created a loop here for I in national income. So for every value in this national income array here, dump it into the aggregate expenditure function, C plus I plus G plus X minus IM, and then find me the value. And then it's going to append it. So it's a loop. It's going to do that for national income equals 0, national income equals 100, 200, and on and on. And it's going to dump it all into this X. Okay, so we made X empty, so we could put our loop in. That would then just keep adding it in to X. So I run the loop. It takes all these national income values, finds the aggregate expenditures for that, and then I have it output those values. So you'll notice here that these values, 300, 350, 400, 450, 500, all the way to 700, they actually match what is here in this last column. So we've actually created this last column of this table by using not this data here, but the formulas that are associated with consumption spending and investment spending and government spending and net exports. So you don't have to start with a table of all these points. You can instead, if you start with formulas, find the formula for aggregate expenditure and find the values. So let me go back to our loop here at the very bottom. All right, so we had our formulas. We used our formulas to find aggregate expenditures. We used a loop to find all of the values for aggregate expenditures, which means we can then plot it. So plt.plot, national income on the horizontal, X here on the vertical, because we assumed we didn't have the aggregate expenditure data from the table. So we found it from the formulas. And then we want to plot it against the 45-degree line, just like we did in the first video, to find where this economy is at equilibrium. So plt.plot, first we plot the X's we found, then we plot national income versus itself, and we run that. And so we can see here that we are at equilibrium when national income is 600, total spending is also 600. Now, we do all this to find the spending multiplier. So when we talk about the spending multiplier, what we want is to know how effective a change in autonomous expenditures are. So for example, if the government stimulates the economy by spending $1 million, how much does that grow and ripple through the economy, and how much does that create in terms of economic growth? If you have a multiplier of 2, then that means that if the government spends $1, income will change by 2 times that amount. So government spends $1 because people's income increases and then they spend and it becomes somebody else's income and it ripples through. The actual impact is twice that. Government spends $1, income collectively increases 2 times that. The first dollar is the government hiring people, and then the second dollar is that ripple effect. So we use this to help us figure out how much government stimulus, we're using a Keynesian approach, should be used to help grow the economy. How much does the government have to spend to create 5% economic growth? So that's going to depend on this multiplier. To find the multiplier, we can use the formula 1 divided by 1 minus MPE, the marginal propensity to expend. This is the slope of the aggregate expenditure function. Now you can also find MPE, not just from the graph, but if you have the marginal propensity to consume of disposable income, if you have the marginal tax rate, and the marginal propensity to import. We've actually found all those throughout this process. So if we actually just scrub back through, we can pull that information here. So mind the scrolling, but let's go find MPC sub D. That was under this disposable income section, and there was a typo, so this should say MPC sub D, a 0.75. Your version might be missing the D. So here we have MPC sub D of 0.75. So that's this right here, 0.75. 1 minus the marginal tax rate. So we could go back and we found the tax rate because the marginal tax rate is the slope of the tax function, which was 0.2. So we have 0.75 times 1 minus 0.2. And then, so 0.75, 1 minus 0.2, minus MPM, that's the marginal propensity to import. That's the slope of the import function, which was 0.1. So we could do this calculation here from our previous videos, 0.75, 1 minus 0.2, minus 0.1, and you could find MPE. We can also find our MPE because we just created the aggregate expenditure function right here. And the slope of this is MPE. So we can take our aggregate expenditures that we just calculated and our national income, and we can use our linear regression to find the slope. So NI needs to be reshaped because it was back in its old form, and X needs to be an array. Then we use our linear regression. Then we have it give us the coefficient. This is the slope. It can give us the intercept as well. And so we end up with aggregate expenditures equals 300 plus 0.5y. We found that here from our formulas. We found that in the first video from the table. So when we had the original data set, you'll recall we found that same formula from the table of data. So from the table of data or from the formulas, you can find the aggregate expenditure function, and the slope of the aggregate expenditure function is MPE. Once you have MPE, the multiplier is 1 divided by 1 minus MPE. So we simply need to do a calculation here. 1 divided by 1 minus 0.5, or 1 divided by 0.5 gives us the multiplier. So if you're doing that in Python, I'll just go back down to the bottom here. We had our formula here, 300 plus 0.5. We can have it calculate the multiplier. And so we're going to use that lambda function again. And here, the variable is MPE. And so we're saying the multiplier is equal to 1 over 1 minus MPE, where MPE is the variable. So if you put that in, then that means you can have it calculate the multiplier for any MPE you give it. And here we know the MPE is 0.5. So we say, give us the multiplier if the MPE is 0.5, and we get a multiplier of 2. 1 over 1 minus 0.5 is 1 over 0.5, which is equal to 2. So we have it do the math for us. The nice thing about this is that if we happen to get a different MPE, we could then have it calculate the multiplier with the new MPE. What this allows us to see then is how much the slope of the aggregate expenditure function changes the multiplier. So notice if the MPE is higher, then the multiplier is bigger. If the MPE is smaller, the multiplier is smaller. So in order to decide how much the government needs to spend to stimulate the economy, we need essentially the slope of this aggregate expenditure function. We need to know of national income, so for every additional $100 of income, how much collectively will we spend? If we spend more of each dollar of income, then it multiplies more and the government doesn't have to spend as much to stimulate the economy. So a higher multiplier, the government spends less to get a greater impact. The lower the multiplier, and therefore the lower the marginal propensity to expend, the slope of this, then the government has to spend more to get the same effect.